In a previous video, we were talking about an autonomous differential equation, y prime equals y squared minus 4y. We started our exploration of this differential equation by graphing the differential equation rather than the solution to the differential equation. I think I'll do that as y prime. So we're going to graph y against y prime. I'll just go ahead and reproduce that graph rather than take the time to do it on screen. And then from this graph, we were able to identify a couple of equilibrium solutions. Let's try that again. And some behavior of the graph. So we have an equilibrium solution at y equals 0, another equilibrium solution at y equals 4, and then in between 0 and 4, we noticed that between what, because this is y, right? This is the y-axis. Between 0 and 4, the slopes, this is the graph of y prime, so this is the graph of the slopes of y. The slopes of y are negative and small, negative and large, and then they get negative and small again. Each one of these little marks is meant to represent a very small segment of a line that would be the slope of the curve of y at the point x equals whatever this x value is. If you squint a little bit, you can see the pattern of what the curve would look like based on its slopes. So let me do the next piece here. When y is greater than 4, slopes are positive. They start small and get bigger. And when y is less than 0, the slopes are also positive, and they start small and get bigger there as well. So they're positive, but they start small and get bigger and bigger, steeper and steeper. They're starting small here, but as y gets bigger, as y gets farther to the right of 4 or greater than 4, farther away from 4, they get steeper and steeper. So each place on this graph now then is, let's see, I'm trying to find a good color to use here. I'm learning there really isn't one. Yellow and white are the only ones that show up really, really well, so it's kind of hard to pick a good color. Let's pick an x value, and then let's follow that x value up, and if depending on which particular solution we end up looking at, let's say this is about x equals 1, and let's follow that up to a place where, I'm just going to circle one here, the curve goes through or it touches that line segment, right? That means that the curve is essentially going to sort of just touch on that piece right there, and then it's going to bounce off and do something else, right? The slope of the line tangent to the curve is the green line here. The slope of the line tangent to that curve is represented by this yellow segment here. That is the tangent line, and it has a slope, and it's small. It's negative. I'm looking at this sideways at the moment. It's negative and relatively small. Farther along, if I were to trace this curve, if we keep going along this curve in the direction that this segment sort of points me, then I'll end up over here somewhere until I get, say, for example, to this place. And there, keep my curve going, right? At that point, the curve is just touching this line segment. Actually, that's the line segment that's just touching the curve. I'm just realizing that I could have done a better job with that. So I've backed out of it rather than erase, because you can't see it if I back out of it, but it also, if I erase, it leaves a mess on the screen. So I'm looking at this line segment now, and I'm looking at what the curve did. This line segment sort of tells me the curve touches this, but its slope is negative, so it's decreasing at that point until it gets to a place here where it's got to touch another line segment, maybe not that exact one, but one very much like it, And at this point, it's still decreasing, but less steeply, right? Here, the slopes were negative and small. Here, they're negative and small. And in between, they're negative and steeper. This curve might even have looked more like that. Oh, I don't know. It's hard to draw on this and not make a mess. So the point, though, that I want to make is that what we've been doing up to this point, you can see if I trace my curve, I follow this curve in the direction, this line segment sort of points me back to here, to a place where the curve still has a negative slope, but even less steep. And eventually, it'll have a slope that is as close to zero as we can possibly make it without actually being zero, right? And yes, of course, there are also these solutions, right? The equilibrium solutions. But the solutions in between are asymptotic. A solution above y equals 4, for example, might look like this, touching this segment, following that general direction, touching this segment, following that general direction, till you end up touching that segment, and so on. Now, the point I'm trying to make here really is that we've kind of been doing this all along, but we've been doing it very informally. We're going to be taking a look now at a technique for estimating a solution to a differential equation if either we don't have the tools that we need to solve the differential equation explicitly, algebraically, or if we just don't want to, right? Maybe we don't need an exact answer, we just want an approximate answer. And the way we're going to do that is this. We're going to pick one of these line segments, not like pick this one here or pick some other one, but we're going to be looking at what the slope tells us about the change in the position of the curve, the change in height in the curve over the change in the run, right? The change in the rise over the change in run, which we think of as slope, right? We think of slope as rise over run. That's what we learned in elementary algebra. We also think of it as delta y, change in y, over delta x, change in x. And now we know to think of it as dy dx for instantaneous change. Right? So we've kind of been working up to this all our algebraic careers. We know about the slope of a line, call it rise over run. A little bit later on, we called it delta y over delta x, the change in the height over the change in the x direction. And actually, I should point out that this could also very nicely be replaced with delta y delta t, or dy dt, because oftentimes what we're looking at is the change in the population over time, or the change in the amount of money in a bank over time, right? So time is often, not always, but often the independent variable. So what we're going to do with this section is we're going to be looking at something called Euler's method, but Euler's method is basically just a formalization of what we've been doing already, right? We're just going to take, we're going to figure out what the size of a change is, and we're going to use that information to help us step through a couple of iterations and figure out what an approximate solution is to a differential equation. In order to do this, I'm going to take another step farther back and look at an even simpler differential equation, y prime equals y. And the reason I'm doing this is one we could easily find the solution for algebraically, but I want to use it to show you what's happening in Euler's method, and then we'll use it to explore a more difficult problem. So if I graph y prime equals y, what I'm saying is that if I know y, I know the slope of my function for that value, right? Let's see, I'll use a different color of pen here. So let's create a slope field. If y is 1, for example, then my slope is going to be 1. regardless of x, my slope is going to be 1. If y is 2, my slope is going to be 2, steeper, and so on. In fact, if y is, in fact, let's do this. My slope is 1 all the way along here, and 2. And if y is negative 1, my slope is negative 1. Negative 2 is negative 2. This is a very simple differential equation, right? We could actually solve this one fairly easily. In fact, we have. The pen has just stopped working. Okay, that is not the prettiest slope field I've ever drawn. When y is 0, slope is 0. Okay, now this is what we've done so far. This is all we've done so far. We've said, let's take that and then let's estimate what the graph looks like by picking some random starting point and following along from, say, 0, 1. What direction must the curve be pointing in? If the slope is 1 at this point, then it must be getting steeper here, and so it ends up looking something like this. And as you can see, I didn't catch all of the lines here, the potential line segments, but there it looks like it has about a slope of 2. And then back here, the slope gets, wrong color, the slope gets shallower again. So it kind of looks like we have an exponential here. And in fact, that's exactly what it is. If in addition to my differential equation, from which I can create a slope field, I have an initial condition, right? If I know, for example, that y of 0 equals 1, then I can pinpoint a specific solution. In fact, that's the one I've used. Let's go with pink this time. This is my initial condition. When x is 0, y is 1. And that tells me it's not this solution or this solution or this solution, but this particular solution, because it goes through that point and not some other point. This is the particular solution that I'm looking for. So now what I'm going to do is I'm going to blow this up a little bit. I'm going to zoom in on this area right about here. So just mostly the first quadrant and maybe the first 2 or 3 values of x. I'm going to create a new graph over here that represents that. So we have our initial condition, when x is 0, y is 1. And we also know something about the slope of our function. At the point where y equals 1, we know the slope is also 1. And so we have a change in our graph of, from this point here, we're going to go, I should point out here that my scale is different in this direction. That's a 1. That's 1. And that is also 1. Because I know this graph is exponential. I wanted some vertical space to be able to do this in. So this graph is going to go from here, from this point here, I'm going to need to go up 1 and over 1 to get to the next point, right? Now that won't be the right point, but it'll be close. And that's kind of the point, no pun intended, that I want to make here. If I have a slope of 1 at y equals 1, then my graph is going to behave something like this, perhaps. And that's because the slope of the function, y, is the same as the y value, right? The slope is the same as the y value. So here the slope was 1 over 1, because the y value was 1, or our starting point was 1. It's actually more likely to be, probably be better if I started back here and used the average. So starting at negative a half and going to a half, I used that rise over run, but it doesn't matter. This is going to get us where we need to be. We're also not going to be using such big spaces when we actually do this, using the technique once we've learned it more formally. But for now, what this does is gives us a new point on the graph, right? So this is the point 0, 1, and we had that. That was our initial condition. We were given that. But when we go up 1 and over 1, we end up at the point 1, 2. So now we have a new y value. As well as a new x value, we have a new y value. And the new y value is the slope at that point. So now I'm going to draw another rise over run diagram that goes up 2 and over 1. So let's go up 2 and over 1. So now I have a new point here. So this triangle is taller, but not as, but the same length, if you will. So that's going to put me here. This is meant to be a straight line segment, just as this was before I drew the yellow curve. That was meant to be a straight line segment. So now I have another point here. This is the point 2, 4, because now I've gone from my original point. I went up 1 from 0. Sorry, I went up 1 from 1. That gave me the 2, and over 1 from 0. That gave me this 1. Then I'm going to go up. I now have a slope of, let me write in here. For this segment here, my slope was 1, and for this one, it's 2. So to get to this next point here, I had to go from this starting point, a slope of 2, which is 2 over 1. That gives me 2 added to the 2, that's the 4, and 1 added to the 1, which is 2. Let's do one more of those. I now have a new y value again, and that y value is 4. If my slope is the same as my y value, then this time I need to go up 1, 2, 3, 4, and over 1. So now my triangle is very tall indeed, and a straight line would look something like this to get me to this new point. Well, that new point has added 4 to this 4, so now I'm at a height of 8, and it's added 1 more to my x value as well. So you can see the pattern here. In this particular one, it looks like we're just doubling our, adding 1 to x. Where am I? Adding 1 to x and doubling y, right? That's exponential growth. And that's exactly what we expect, because we know from previously having worked on a problem like this that we're going to get an exponential function here. And in fact, if you squint and you're not looking for straight lines here, but you're looking for more of a continuous behaving curve, and you're going to see that exponential in here. This is an approximation. Okay, so what good is this? Well, if I know the differential equation, and I have a set of initial conditions, then I can use this technique to estimate y of some other value, let's say 3. And we've already done that. In fact, it's 8. That's an estimate, but it's 8. Now, as it happens, it's actually a very bad estimate, because we know from our previous work with this very equation, this differential equation, that the general solution to this equation is y equals k e to the t, or y equals k, I guess I'm using x. I'll use x. Y equals k e to the x. And with these initial conditions, with this set of initial conditions, it turns out that k equals 1. So we actually have the equation, the solution to this, the particular solution to this differential equation with this set of initial conditions is y equals e to the x. Well, y equals e to the 3 is approximately 20, not 8. So we're way off here. But the reason we're off is that we're using step sizes here that are too big, right? We're going too far away from the actual graph before we take the next step up, and then too far away. We're actually diverging from the graph instead of getting closer to it. So that's the reason our approximation in this case wasn't very good. But if we use smaller step sizes, then we'll get a better approximation. So we need to address the step size, but we also need a slightly less cumbersome way to do this. You're not going to want to plug each, value in first, find your second y, and then reevaluate what your new y value is going to be. We kind of want to build a formula here, ideally. So let's take a look at what we're actually doing every time we use one of these line segments. This line segment right here is just a piece of a much bigger line, right? If I draw my line off like that, of course it keeps going forever. And I can come up with the equation for that line. We know the equation of a line is y equals mx plus b. And I should probably also point out that this initial condition, we often label this x naught, y naught. And so that first y value there, the one that I was given as part of the parameters of the problem that I'm trying to solve, that's my y naught. And what I'm trying to do is get to this next y value here. So I'm going to call this y value y naught, and this y value y1, comma in there. So what I need to do is to get to y1, I need to figure out what my slope is and multiply it by some x value and add that to some constant. Well, the constant is the y-intercept, right? The b is our y-intercept. And if you take a close look at this graph, you can see that the y-intercept is my original y value, my y naught. So I'm going to put a y naught here. And all I have to do now is figure out what my slope is and what my x value is. Well, the slope is, conceptually anyway, I hope you feel that the slope is easy, because the slope is dy dx. It's whatever dy dx is. And remember that this can be a function of more than just or more than just y, right? This is a homogeneous, no, not a homogeneous, this is a autonomous differential equation, but we can have a dy dx that's equal to functions of x and y, or t and y. So I'm using x and y in this example. So I'm going to call that function, let's see, where will I put this initially? This function here is normally a function of x and y. So that's my slope, because that is that, whatever that is, whatever function is in that position, that is my slope. That's my dy dx. So this is going to be, I'll erase my box here. This is going to be some function of x and y. And importantly, because I'm looking for this y value, I have this y value, I'm looking for the next one over, it's going to be the slope that's associated with this point right here. So it's a function of x naught, y naught. It's a function of that particular x and y values. Okay, now I need to move this plus y naught just over a little bit. Plus y naught. Because I need to find a way now to express this x. And this x also will depend on where I am in the process. So right now I'm working on finding this second point. So I've started from my try to get the pen in the right place eventually here. I've started from my first point and I've moved up and over, that's my m, times some distance across, right? I'm kind of multiplying each slope movement by whatever this distance is. And so in this case, it's going to be this 1 here minus the old x value. So 1 minus 0 is 1. And of course, this will be 1. And then when I multiply that by anything, it returns the same result. So that's why we didn't see that in the initial version of the problem that we did. Now, I've written the slope in a very generic way, but I've written this the step size in a very specific way for the previous example. I need to make this more generic as well. And in order to do that, what I'm going to do is just look at the two values that I have here, this 1 minus this 0, and say, well, what if I was way over here somewhere? What would I be doing to get that same step size? I'd be taking whatever this x value was and subtracting whatever this x value was. Well, whatever this x value was, this is the next one up. So if I'd already had this one, I could be working on this step here. So if I was up at the nth x value, then instead of 1, I'd have x sub n, and I'd be subtracting 1 less than that. So actually, I can write that as the value I'm going to be working with now minus the one I was working with a minute ago. So x minus x naught here is the value I want to find the new y value for, the x value that goes with that new y value, minus the one I had before. Well, this particular one happens to be 1, and the old one was 0. The old y value was 1, and I'm looking for the new y value, and my function here is just going to be y. But to generalize, get rid of all of these things again, to generalize, this is the beginnings of the formulation of a formula. Not quite there yet. I want to tidy things up a little bit. First, I'm going to rewrite it in the order that your book uses, just because I think that it will become clearer. They've got this plus y naught at the front. So instead of a plus b, they're writing it as b plus a. So y naught plus, we have a function in x and y, I'm leaving some space for subscripts there, times t minus t naught. Oh, the textbook uses t, and I was contemplating off camera there whether I should go with that or not. I decided not to, but then I wrote it that way anyway. X minus x naught. So, and I'm going to write my subscripts in as well. So for the first y value after the given one, this is my 0th y value because I was given it. For the first one after that, take the old one and add to it, that's my b, that's my y-intercept, add to it mx, where m is the slope of the function, right? It's the slope of the line. It's the slope of the line starting at this point and ending at this new x value, this new y value that we want to find. That slope, which is a function of x and y because it's a differential equation, it's a dy dx. So that's going to be my slope, times x minus x naught. And x minus x naught is the distance between my starting x and the next one over. Now, if I generalize this, I'm going to get that the nth y value is equal to the y value before that plus a function of x and y times the difference between two x values. Now, which two x values should we use? Well, if I'm all the way over here, this is 1, 2, 3, 4. It's going to be 4 minus 3. So if I'm at my 4th x, right here I'm at my 0th x, here I'm at my 1th x, my first x, my second. If I'm at my 4th x, that 4 represents the number of iterations that I've been going. So this is going to be x4 minus x3, my new x value minus my old x value, except it's not necessarily 3 and 4, just erase the whole thing. It's whichever one I'm looking for. My pen takes frequent breaks. Minus the one before that. It's an n minus 1 there. And this, the slope that I'm using too, this function of x and y, the slope that I'm using is the one associated with the old point, right? I'm looking for a new y value, and the only way to get there is to go in the direction that the curve's tangent line tells me to go at the old point. So I'm going to have a y sub, I'm going to do it slanted here because I'm out of room, n minus 1, n minus 1. So we're going to take our old slope and our old y, and then we're going to take our new x and subtract our old y, and combining those in this way, it's going to give us our new y. Now your textbook does it slightly differently, and I think I kind of see why. These subscripts get in the way quite a bit here. So what if I said, well, let's talk about, instead of the old one and the new one, the current one and the one before, what if I talk about getting the one that's next in line? So basically I'm just going to add 1 to all of these subscripts. I'm going to have a function of x sub n, y sub n, and x sub n plus 1 here minus x sub n. So I'm still taking basically my new x value, and that's supposed to be a minus there, not a comma. Okay, minus. My pen's taking another break. There we go. So I'm taking my the new x value that I want to work with and subtracting the old one. That difference right there is the difference between these two x values. That's my step size. I'm multiplying that x by m, the slope, and I'm adding the y-intercept. My new x value minus my old one. My old slope, I have to get this point, I have to use this slope. To get this point, I have to use the slope from here, right? The slope at this point was this line right here, the slope of that line right there. So I'm using the slope from the old line to get the new point, and that's the slope from the old line there. And I'm using the old y-intercept to get my new y value. So apart from the fact that they use a t instead of an x here, this is the form this formula is in your textbook, assuming that you're in my class and not just watching this for fun. They use t here instead of x, but apart from that, that's the formula they give us. And that's where this formula comes from. It's just the equation of a line. I will also point out, I'm going to erase, well, no, I think I'll leave it there. I'll also point out that some textbooks use the form y sub n plus f of x sub n y sub n times h, where h is understood to be the step size. My handwriting is all of a sudden very messy today. I have no idea why. And by step size, we mean x sub n minus 1, or x sub n plus 1 rather, minus x sub n. That notation, so this notation here, this h, really is just this difference here. And this textbook just outlines it explicitly, or it states it explicitly. We're looking for this difference of two x values. But whatever that is, it's going to be the same for each step, right? The same for each iteration that we do. So once we know what that is, it's going to be the same in every iteration of the problem that we work. I think I'm going to erase some of this stuff down here because that's not really the one we're going to be working with. I'd like to take just a moment and do this same example that we did a minute ago, using a smaller step size, but also using this formula. And I'm going to do that by making a table. Okay, so this column N here is the which iteration I'm on. So over here I had iteration 0 was I just knew what my x and y values were. I was given a starting point. Right? I was given initial conditions. So that was my n equals 0. And at that point, I know that y equals 1. I happen to know that x equals 0 and y equals 1. I also know, since my equation is y prime equals y, that whatever y is, y prime is the same. Well, y prime is just my f sub n, right? It's my slope function. So in this case, if since I have y equals 1, I also have f equals 1. Okay, I've added a few things here. A very abbreviated version of my formula down here. I have that my new y value is going to be equal to my old y value plus f sub n is just the f function at the nth xy pair of values, right? Times h, which I said this difference is often referred to as h. I've just noticed actually your textbook does something different here again, but I'm going to stick with this explanation. I think it's a little bit easier. So if I know my y sub n and I know my f sub n, I know my slope at that point, and I know my h, then I can figure out what my next y value is. And once I know what that is, I can plug it in here for my next iteration. The problem is I don't know what h is. It's usually specified. If it's not, then it'll be your job to decide on a small enough h value that you'll get an accurate estimation without it being so small that you'll have to do a million calculations to figure out what your answer is. So for the sake of argument in this example, I'm going to say let's let h equal 0.1. Oh gosh, see that I've just done exactly what I wanted to avoid. That's to get to this place here where x equals 3, I'm going to have to do 30 computations, right? This is 1/10 of 1, whereas when I was doing 1, 2, 3 before, I'd have to do 10 in each of those spaces. I'd have to do 30 computations, and I'm not going to do that. So again, for the sake of brevity, that would give me a more accurate value than what I'm going to use instead. But for the sake of time, I'm going to stick with a larger h value. Okay, so I'm actually going to need to do more than just 3 computations as well, but maybe I'll just compare after 3 and we'll see what happens. So now I know my n value is 0. I'm on my 0th computation, my 0th iteration. I was given 0 and 1 for x naught and y naught. I know my slope from my equation here, and I'm going to plug all of these things in to my formula. So I've got y sub n, which is 1. Nope, y sub n, which is 1, sorry, plus my slope at my 0th iteration, which is 1, times 8, which is 0.5. So I'm going to have y sub n plus f sub n at that point times 0.5. And that is equal to 1 plus a half, which is 3 halves, or 1.5. Now, this is my y sub n plus 1. So in my next iteration, that becomes my new y value, 1.5. I've copied this table from your textbook because of the way they set it out, because of the way they've written their formula. They need this x column. I don't think we need it. So I'm going to carry on without using that, because all I'm looking for, if what I want to do is estimate y of 3, then I'm looking for a y value for a particular x value. So do I care what x is? I suppose I do, because I need to get up to 3. So I guess I'll write down x sub 0 is 0, x sub 1. How am I going to get that x value? Every x value is half a unit over from the one before. So I'm just going to make this column here by adding a half to each x before it. So that's going to be 1/2. I guess I'll write it as 0.5, and then 1, and then 1.5, and then I'll see if I want to do any more. All right, now I have my new y value. So what is my slope at that point? Well, it turns out because of the equation that I'm working with, the slope is the same. So I can just use 1.5. And now I can work out my new y value. It's going to be my old y value, in this case that's 1.5, just the one before, plus my old slope, the ones from this row, right, is going to be 1.5. And I'm going to multiply that by, forgot my decimal point there, by 0.5. And that gives me 2.25. I think I better erase this vertical line here. It's going to get in my way. 2.25. That's my new y value, so I can put it down here. As it happens, my y prime, my slope, is the same as my y value. So my new y value is going to be my old y value plus my old slope. I guess I should call them my current slope. My new y value is going to be my old y value plus. My next y value is going to be my current y value plus my current slope times 0.5. And that gives me 3.75. No, as it turns out, 3.375. Oh, this pen. There it is, 3.375. Okay, I'm going to do 2 more here because I want to get farther out than just x equals 1. But I don't want to go all the way out to x equals 3 because I need 6 iterations. I'm not going to take your time or mine to do that. So let's add a 4th iteration. And let's perform our 3rd and 4th iterations. So this is going to be 2. I have my new y value, 3.375. That becomes my current y value, 3.375. Because my slope and my y value are the same, I have 3.375 here. And then I have my current y value plus my current slope times 0.5, which is 5.0625. I think I'm going to go with 5.06 just because, oops, because otherwise I don't really have room to write the whole thing. My new y value, 5.0625. I will say that while I'm writing this abbreviated, this truncated value, I'm going to continue working with the full value, which is 5.0625. I'm going to stick that in my calculator right now in the memory. So my now new y value is 5.0625, and so is my slope, 5.0625. And so my next y value will be 5.0625 plus 5.0625 times 0.5. And that is 7.59375. Okay, so we now have an approximation for when x equals 2, y is about 7.59. If we look at the graph that we created here, doing this the first time, when x equals 2, we found that y was approximately 4. Well, here we're getting y is over 7.5, closer to 8 at x equals 2. To be clear, when we found that y equaled 8, it was previously was at x equals 3. Well, we were estimating, right? But again, that was with a step size of 1. Now we're working with a step size of 1/2. I didn't mark this on the graph. Let's just graph this real quick here. If I have 0.5 and then 1.5, and I'll use a different color of pen. Maybe, I don't know what the best color is. Struggle with this. Let's try the green one. We had our original given point was y equals 1. Then at x equals 1/2, we got y equals 2.25, which is a little higher than our step size of 1 gave us at x. Oops, I put that at 1, not 1/2. So right about there. When x equals 1, we got 3.375. So now we're up at 3, 1, 2, 3, not quite 4. So we're there. So that's actually smaller. Then at x equals 1.5, we ended up with y equaling 5.06. At 1.5, there's 4, 5, just over 5, so we're about there. And at x equals 2, we got 7.59. I don't even have that on here. Let's see, that's 5, 6, 7. It's just right about there. So interestingly, and this is not something I pointed out earlier, but it's worth noting that this value is exact. This value is over the previous estimation. This value is under the previous estimation. This one's over, this one's under. I think that's quite interesting. But each one is closer. And so this graph would look something, wrong pen color there again. This graph would look something like this. Okay, I think I'll redo that last one. Okay, and then let's take a look at, just very quickly, in yellow, what the graph of the actual values that e to the x goes through. So, of course, we have e to the 0 is 1. E at 0.5, e to the x, e to the 0.5 is 1.65. So we'll say that's 1. That's about there. At 1, of course, we have e, which is about 2.7. So we have 2, 1, 2, almost 3, about maybe about there. I'll do the others off screen.